Before I discuss case 2 on the proof of this result, and if you remember what we were trying to prove is that if we have an inscribed angle, such as shown here, that the measure of the inscribed angle is exactly 1/2 the measure of the central angle. I don't want to use that. 1/2 the measure of the central angle, which is this angle right in here. So the central angle is the angle that we measure uh, with the lines going to the center of the circle, and the inscribed angle is the angle that we measure with the lines going to the edge or the circumference point of the circle. Um, and So we've already proven case 1, that's this case right here, where one of the lines actually goes through the center of the circle or is a diameter of the circle. Now before I move on to prove case 2, I want to mention a convention that I will be using when I'm talking about arc lengths and angles included by arc lengths. If I refer to, for example, this arc length right here uh, being an arc that circumscribes a 30-degree angle, what I always mean when I talk about that is it's the arc of the central angle, not the arc of a inscribed angle. So it's not this one, okay, it's this one right in here. So if I talk about this arc being 30 degrees, I'm talking about this central angle right here. Now with that, let me go to case 2 of the proof here. Case 2 is when we have the center of the circle is not on one of the lines of the inscribed angle, but rather is interior to the inscribed angle as shown right here. Now, remember, we've already proven it here for case 1 when one of the lines goes through the center of the circle. So here's an expanded view of case 2. Okay, here we have the center of the circle. Here's the inscribed angle. So in order to prove this, it's actually pretty straightforward and we use case 1 to prove case 2. So I will draw this line right here, okay, and have that line be a line that goes right through the center of the circle. So that's a diameter of the circle. Now, I have already proven that this angle right in here, this angle right here, is 1/2 of this angle. So if I look at this angle right here, this angle is twice this angle. I've already proven that in case 1. Okay, in a similar fashion, I have already proven that this angle right here is half of this angle. Okay, so using case 1, I've proven this angle is twice this angle, and this angle is twice this angle. So for example, if I call this angle X, call this angle Y, this angle here becomes 2X, and this angle here becomes 2Y. Okay, and I've done that using case 1, which I have proven previously. So that means that the sum of these two angles, X and Y, which is the entire angle right here, this is the sum of angles X and Y. So I have X plus Y is that sum, which I'll write. X plus Y is now this inscribed angle. Okay, so this is the inscribed angle right here. And this central angle that covers the same arc is 2x plus 2y. So the central angle is 2x plus 2y. So I write this central angle So this is the included angle, or the inscribed angle, sorry. And this is the central angle. And I think it should be pretty clear and pretty easy to see that this angle right here is equal to 2 times x plus y. So this angle is twice this angle. So we have proven case 2 that the central angle here is twice the inscribed angle, which was what we were trying to prove. Okay, now the third case, case 3, I'm not going to prove that except to say that it goes exactly the same way. The proof of case 3 goes exactly the same way as we just did in case 2. In this case, we draw this line going through the center of the circle, and now we have to deal with this inscribed angle and this inscribed angle. And again, just as we just did with case 2, we look at the included angle here. I'm sorry, the central angle there. Okay, so I'm going to let case 3 be for you to think about. Like I said, the proof goes exactly the way we did it in case 2, where we used the result from case 1. So if you can do case 3, I'll be very happy that you understand how this proof has progressed. Okay, next time.